Okay, so a series that comes up quite a bit is called the Harmonic series. And this is what this series looks like from n equals 1 to infinity of 1 over n. If we write out some of its terms, when n is 1, this is 1, plus a half, plus a third, plus a fourth, plus a fifth, and so on. Nth term is 1 over n, and then this keeps going. Now the question is, does this series converge or diverge? It's not a series for which we can find the sequence of partial sums. And so we can't actually find its actual sum, but we can determine whether it converges or diverges. And so I'm going to just explain an argument that a mathematician called Oresme did, a French mathematician. And to do his argument, I'm going to write out various terms of this series and show actually why this series diverges. So let me just take a moment to write out some of these terms. I'm going to write out 16 of them. 17. Oops, 15. And so on. And so the argument goes like this. We have the 1 and the 1/2. If we take a third and a fourth, we know that this sum is greater than 1/2. We know this because a third is greater than a fourth, and a fourth plus a fourth equals 1/2. Since a third is bigger, this sum must be bigger than a half. And then he went ahead and grouped the next 4 terms and said those 4 terms added together are also larger than a half. We know that's true because if I take 4/8, right, an eighth plus an eighth plus an eighth plus an eighth, that's equal to 1/2. But a fifth is bigger than an eighth, a sixth is bigger than an eighth, a seventh is bigger than an eighth. Therefore, this sum must be bigger than a half. And he kept doing this, grouping terms of the series that are adding together and showing that those always had to be larger than a half. And so what's happening with this series is that we're always adding, even though very slowly, adding groups of terms that are going to be larger than a half. So this will keep growing and growing and growing. Very, very slowly, but keeps growing. And so this series diverges. So this is important to know that the harmonic series always diverges. The second idea that I wanted to discuss in this short video is something called the nth term test for divergence. So let me explain what that says. So this is the nth term test for divergence. It's a test that we can only use to show that a series diverges. And it says the following. It tells us that if the limit as n approaches infinity of the nth term of the series, the nth term, if that's not 0, then the series diverges. So this is the test. So a short explanation here is as follows. You know, when we have a sequence, we determine whether it converges or not by just taking a limit as n goes to infinity. When we start adding those terms, though, if, as we're adding terms, the only way that the series can converge is if those terms that we're adding don't add up indefinitely to larger and larger and larger values. So we look at the nth term, and if those don't go to 0, then the series diverges. It's growing too big if the terms ultimately don't go to 0. Let me explain what this does not say. So I'm going to write a statement here. This does not say that if the limit of the nth term is 0, that the sequence converges. That is not the case. The series could still diverge. So this is not the case. This only works if you show that the limit of the nth term is not 0, then we know the series diverges. But it doesn't say that if it is 0, the series converges, because, well, we know that for the harmonic series, which is a divergent series, we can see that the limit of the nth term as n goes to infinity of 1 over n, that is 0. But this series is divergent. So the only way we can use this test is if we can see that the nth term is not going to be 0, then we can say the series diverges. Let's do a couple of examples. So let's suppose we have the series from n equals 1 to infinity of, let me find a good example, I don't know, something like 2n squared minus 1 over 3n squared minus 1. Now, if we just look at the nth term, we can see that when we take the limit of the nth term, 2n squared minus 1 over 3n squared minus 1, as n gets really large, this tends to 2/3 because the dominant term in the numerator has the same power as the dominant term in the denominator, so this will go to the ratio of the coefficients. This is not 0, which means that this series diverges by the nth term test. Because what's happening is that further down the line, the terms are getting too big, and so the series is going to blow up, right? So because the nth term doesn't go to 0, the series diverges. Another example that we can look at is, let's suppose that we have the sum from n equals 1 to infinity of 6 plus 8n plus 9n squared over 3 plus 2n plus n squared. Well, if we look at this series, it's hard to know what's going to happen. It's not geometric, it's not telescoping, it's not the harmonic series. So right now, all we can think about is, well, what happens when we take the limit as n goes to infinity of the nth term of this series? Well, those terms are getting too big because in the limit, this goes towards 9. 9 is not 0. And so we keep adding terms that are getting too big, and so this will diverge by the nth term test for divergence. So again, nth term test for divergence only tells us when a series diverges. It doesn't tell us whether or not the series will converge. So if the limit is 0, the series could converge or diverge, as we saw with the harmonic series.